Super excited to be here today. I think that a lot of changes that are occurring today in how we look at data are really important for us as an industry. And in particular, how we look at databases and how we store our data and how we access our data. And graphs is obviously the model which I love the most. But every type of database has their place, and so we're going to be talking about that here today. So this is about RDBMS to graph, and to start off with, we just want to talk about where we've come from as an industry. You know, we started off storing data in punch tape or punch cards, and obviously this is a horrible way to read and understand our data, but it was the technology that was available at the time. We advanced as an industry, and we started storing our data in tables of columns and rows. And these tables many times started off as being very human readable, but then as you started having primary keys that were auto-generated numeric keys referencing foreign key relationships, as you normalized, it started to be not so human readable, but it did have some key advantages. And those advantages were around things like data reliability, ACID compliance, the ability to ensure that when you commit a transaction and the system says it's committed, that it really is committed in your data. And that was extremely important and a very strong advance in the database world. Now, the traditional data structure that people have for their applications is storing essentially one relational database per system. So, they have a relational database around their HR tools, around their supply chain, around their payment system, around the logistics system. Their CRM has a database. Their support team has a database. Everyone has a database. And what we've started to see, though, is that we're living in a much more connected world. And we need to think about systems of engagement as opposed to these discrete, separate databases and separate systems. So if we think about it in terms of engagement, how are people engaged with our businesses? We think about how those users engage with their devices, how those users engage with other users, and then how devices engage with other devices. But it's this whole very interconnected world. We're no longer living in this world where we have these data silos and we're comfortable with that. We really want to take advantage of all of the data we have in all of these different systems. So if you look at where we are today in terms of how much data volume we're going to be collecting as businesses, as individuals, as other types of organizations, we've slowly ramped up the amount of data we're collecting over time. But as more and more systems and devices start to get online and start to produce data, and we think of things like data science and data analytics, and we think about how we can make real-time decisions off of our data efficiently with things like machine learning, we're going to be collecting more and more data. So we're here right now, but we have that strong upward slope to still get to. So you can think of systems of record in the relational database model. You have these structured, pre-computed tables based off of somewhat rigid rules. And then if we think of systems of engagement, we think of some NoSQL models, and we think about flexibility. We think about real-time queries, making decisions based off of that data. And we think about a highly contextual analysis of where we're at. And now that's not to say that there's this hard line between the two. You'll find many things that fit into both of these cases. But in general, you want to think about the idea of how do you take advantage of all of your systems interconnecting with each other and using those for real-time decisions that are just making smarter decisions from that data. So we have our systems of record, and we move into a world of systems of engagement. Instead of the silos, we have a graph. And the graph represents how each of the bits of data interact with other bits of data in your systems, regardless of what those systems are, whether they're your CRM or your sales system or your HR system. We want to think about it as one global system of data and how that data interacts. So graph databases have three key advantages for data that is highly connected. First is intuitiveness. And intuitiveness really means that your whiteboard model is your physical model. What we store in the database is the same thing as a business person might draw up on the whiteboard. There's no translation between the business person and a business analyst and a developer and a DBA, because what everyone is dealing with is the same model. You're dealing with your data as a set of nodes and relationships between those nodes. You can think of your nodes as sort of the nouns, as the rows in your tables in a traditional world, and then the relationships are the verbs. It's how those rows interrelate with other rows. Now, speed is actually one of the important things. Brief history of our company is we started off originally when our founders were at a different company doing content management, and they were trying to do like catalogs of photos and the relationship of photos to each other. So if you think about, you search for an animal, you want to get every photo that's tagged as an animal, but you also want to get photos that are tagged as frogs or photos that are tagged as dogs. And you know, there's a hierarchy or even a graph of terms and how they interrelate to perform amazing searches for your users. So our founders actually initially created Neo4j or created the concept around Neo4j on top of a SQL database. And they basically provided a way to perform graph-like queries on top of a SQL database because they thought that it was a much easier way to express them, and they thought that they doing graph operations, they could achieve higher performance. But basing it on top of a SQL database, they didn't really achieve the performance that they were looking for because the expressiveness of querying the data as a graph allowed them to do more and more interesting things with the data. So they hit the roadblock in their analysis, and they decided to build a native graph database. And we're going to start to talk about what that means here soon. But a native graph database is about performance. And this is what a lot of our customers originally come to Neo4j for, is speed. eBay has a great quote here from Volker, who says that we found Neo4j to be literally thousands of times faster than their previous MySQL solution, with queries that require 10 to 100 times less code. Today, Neo4j provides eBay with functionality that was previously impossible. And this really demonstrates the value of a graph and the value of a native graph database, in that you can provide really fast performance, but also make it a lot faster to build your applications because it requires a lot less code. Now, speed. I talked about speed. Now let me talk about why that speed is and what a native graph database is. So what does native mean? Well, when we store data in a SQL database, we store data in something that looks like this, in tables. Those tables have columns, those tables have rows, and it's a great way of representing data when the data does not interrelate. When the data is discrete bits of data and we want to query, for this employee, give me all the information about them, and we're not worried about things like consistency in some of the columns and things like that. It's a great way to think about tabular data. And there are key value stores, and key value stores are great when you have a key and you want to look up a value. That's a fantastic way to do it. And then there are document databases, and document databases are great at storing documents. And there are databases that natively store data in each of these formats. And there are many databases that take these native formats, whether it be columnar or SQL databases or key value databases or document databases, and build on top of them a way of expressing queries using a graph. But that's not the native way that their data is stored. The native way that their data is stored is either as a table or as a document or as a key value, and that affects the performance. So native matters because even if you build a graph way of accessing the data on top of a non-native graph database, the performance is going to take a hit. So you might achieve things like flexibility, you might achieve things like ease of development, but in the end, your performance is going to take a hit. And I'm going to give you an example here with a relational database query. And so you have three tables here. The top left is basically a list of all your employees and some pictures and other attributes of those employees, which we don't need to change over time. And at the top right here, we have the reporting relationship of those employees, which does have a start date and end date, what employees report to what other employees. And at the bottom here, we have the location of those employees' offices, which also would have things like a start and end date. So we want to maintain that as a separate table. Now, what happens if we want to query here? We want to get me a list of every employee and their manager chain and what office and building that employee is in. Well, we end up having a lot of index lookups. So indexes were added to SQL databases as a way to quickly look up data. And it is great if you're looking up an index one time or two times. But in the case of looking through all of these employees and figuring out what offices that they're in, or figuring out what their manager hierarchy is, you're going to end up performing a lot of different index lookups. 16 is what I counted here just quickly. It may be actually more. But you're doing index lookups for each of these employees and then going to their managers, doing index lookup on those managers to find the manager in the employee table to find out their name, etc. And then you're doing index lookups, obviously, to figure out what building and office people are in. So these index lookups that happen on every join operation are quite expensive. A native graph database, on the other hand, gets performance through something called index-free adjacency. So we have an index lookup to determine a list of all of the employee nodes here. And we have that single index lookup. But then from there on out, and this obviously is just a partial view of the data that was represented in the table earlier, but from there on out, we can take those employees and we can figure out who their manager is or what their office is just by traversing those relationships. And we traverse those relationships without doing an index lookup. We traverse those relationships simply by doing pointer arithmetic, either in memory or on the disk, to say, okay, the next node, the next node in this is managed by relationship is, I don't know, 340 bytes away. Go there. And that's a much, 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 much less expensive operation than doing an index lookup for each and every join. So this is really the performance advantage that people experience with graph databases, is this index-free adjacency as opposed to the index lookups in a RDBS. Agility. So agility is about a naturally adaptive model. We say schema optional with Neo4j, and what that means is that you can add and remove these nodes and these relationships on the fly. And every node and relationship has a set of properties associated with them, which you can also add and remove on the fly. So it's adaptive. We are schema optional, I say, because we do have some schema constraints that are available in all editions of Neo, and then some additional schema as constraints that are available in our Enterprise edition, and that's growing. We're going to have more and more types of constraints that we allow you to do in our Enterprise edition because enterprises often demand that. Enterprises need it for compliance reasons or what have you. But the key thing here is that you can adapt your data model on the fly as you need to without doing schema migrations. And then there's a query language that's that's designed for connectiveness. This means that our query language is kind of naturally, it is natively a language designed for querying connected data. So this all goes into what is a native graph database as well, because what it means as a native graph database is we think of everything in terms of graphs. Now, people have layered on top other data models like document data models and things like that on top of Neo4j and built some interfaces for that. But what is the thing that controls our underlying priorities and our underlying focus, and that is making sure that graphs work wonderfully. So we have a query language called Cipher. Cipher is SQL but optimized for graph. So what this query here is, I know it's fine print, difficult to read, but what this query is finding all employees in an organization up to N levels deep in that organization, and basically returning the management chain up to N levels deep within the organization. And they're doing this by a series of union between different queries at varying levels in the organization. Now, I'm not going to claim that this set of queries here in this SQL query is the most optimized. I know that later versions of SQL do have ways to do these kind of tree traversals a little bit better. But these are the types of queries that our customers are coming to us and that they have running in their production systems. These are what their developers are writing, and instead of that query, we converted them into a Cipher query that is 5 lines. So to find a boss and all of the people who report up to that boss and the number of subordinates that report to them is really just 5 lines of SQL, 5 lines of Cipher, as opposed to this hundreds of lines of SQL. So in the end, with a query language that's designed for this connectedness, it basically saves you time, both as you're building it, but also as you maintain the queries and you bring on board new people into your organization. So we, of course, recognize that Cipher is not something that has as many people in the world who know how to use Cipher today, but once they know how to use it, it becomes a lot more powerful and easier to use than SQL for connected data. And you can find, we have a certification program. We've reached over 500 people that are certified and promote their certification on things like their LinkedIn profile. And we continue to get more and more interest in that every day in our training and certification programs because people are really loving Cipher and finding it easy to use. So I never introduced myself. We're 20 minutes into the presentation, so now's probably about time to do that. My name is Ryan Boyd. As Corey said, I'm on the developer relations team here, running developer relations for North America for Neo4j. But my background is as a developer. I developed web applications for 5 years in higher ed, but those were classic sort of business applications, e-commerce and workflow applications. Then I went to Google and worked 8 years on our cloud technologies, including things like BigQuery and other databases. And then I came to Neo, and my email address is at the bottom here. You can feel free to reach out to me if we have questions that we don't answer in the Q&A period that you really want to ask me. Feel free to reach out to me via email there. I'm also on our community Slack channel, neo4j.com/Slack, and you can find me online most of the time on our community Slack channel, along with many other folks on the team. And you can reach out to me on Twitter at RyGuyRG. So we're here for you. We're here to help. We're here to answer the questions that you have. And most importantly, we're here to get you excited about a new way about thinking about data. So use cases. What deals with connected data? Why is connected data important? Let's talk about some of these use cases. Now, I do want to say that everyone in this world hears the term graph database, and I would say 80% of those people immediately think social network. So do me a favor and help us spread the word that graph databases aren't just for social networks, that graph databases have a lot of other really meaningful use cases that help businesses solve problems. So we have hundreds of enterprise customers that have discovered this. But for the thousands of people that are listening to this, please spread this word to your colleagues. So recommendations, real-time recommendations. You can think about the classic recommendations of basing things off of community filtering and basing things off of the actions that people take. So what people bought, what people viewed on an e-commerce website as an example, and then recommending based off of those relationships. This is the most simple way of thinking about recommendations, but you can think about recommendations in a lot deeper ways as well. Deeper in terms of what data sources that you bring together. Some of our real-time recommendations folks in the retail industry bring together things like their logistics system, their customer support system, their inventory system, their products and future products catalogs, and they bring all of this stuff together in addition to the classic types of recommendations to make better decisions, and they can do that efficiently in real time by storing the data in a graph. So you want to think about all the different types of data that you can bring together to make good decisions. And then you also want to think about the types of algorithms and all that you can apply to make those recommendations decisions. Later in this webinar, I'm going to show you the Neo4j Sandbox, V2 as we're calling it. And the Neo4j Sandbox is a way that you can try Neo4j online with various use cases. The V2 one, at least, allows you to try it with various use cases. We give you sample data sets and we give you guides that guide you through it. One of those is a recommendations use case, so I'd encourage you all to check that out if you're interested in recommendations, either retail recommendations or content recommendations or other types. So you could be recommending what doctor for someone to see, or you could be recommending, like the Financial Times, what news articles someone should read, or you could be recommending, like for the top 10 retailers that in the world that use Neo4j, recommending products to purchase. Master data management is bring all of your data together across all of your different systems and look at the users in the context, or look at the questions that you have in the context of all of your data rather than thinking your data in silos. So Cisco uses us for that, as well as a lot of other Global 1000 companies. This is another thing on master data management. They use us at Cisco for a number of different use cases, but one is for their help desk and recommending products as well as articles and support information for people who contact their help desk to basically more efficiently serve them. Fraud detection is naturally a graph. We have people everywhere from the gaming and microcurrency worlds to insurance industries to governments to financial industries using us to understand what fraud is incurred in their network. So they're using us to understand, for instance, are a number of different people using the same address in order to apply for credit? Are people who have relationships with each other claiming a lot of whiplash in insurance cases? So is a doctor signing off on a whiplash injury and at the same time having a whiplash injury themselves and at the same time witnessing a whiplash injury? That's how a lot of these rings work, is they reuse the same people or identities or locations and other entities in their fraud rings, and it's important to detect all of the relationships between these entities. So fraud detection is a very popular use case for us, but as you can imagine, there's not as many public references for fraud detection. I can say that some of the top banks use us, top insurance companies use us, but they're not all public. So, but that said, this Gorka Sadowski is a cybersecurity expert that works with many of those types of companies. And he says, graph databases offer new methods of uncovering fraud rings and other sophisticated scams with a high level of accuracy and are capable of stopping advanced fraud scenarios in real time. Graph-based search, we talked a little bit about this in terms of a content management system earlier on. And in terms of a content management system, you can do things like hierarchy of terms and all that I talked about. But there are many other ways to apply graph-based search. You can actually think of this very similarly to real-time recommendations. It's about how do you get people the right assets at the right time. And it's not just about the content of the data, but it's about how the data or the objects that you're searching interrelate to each other. Obviously, Google is the most famous use case of graph-based search. Their PageRank algorithm relies very heavily and at one point almost exclusively on these rankings, on how all of these different web pages in the world interrelate. So it's a powerful way to think about your data, but you don't have to be Google to do it. You can use Neo4j to do it. Network and IT operations. Sorry, I keep on skipping over these examples. I'm much more about the code than I am about the actual customers here, and much more about the use cases and the power of them than the actual customers. But as you can see, we have some major companies who are doing each and all of these things. Network and IT operations, you're looking at dependency analysis and root cause analysis. Computer networks are networks, networks are graphs. It all works out well together. So if you have a switch that you are taking down for maintenance, in the typical world, you might just notify the people who run each of the machines that are connected to those switches, and they would be responsible of saying, well, here's the applications that run these machines, and the application owners would get notified, and then the application owners would say, well, here are the users that are on each of these applications and rely upon these, and they would say to each of their users that the system is going down for maintenance. In reality, those users hardly ever get notified. The application owners sometimes often don't get notified. The machine owners usually do get notified, but it's a cumbersome process. So why not automate that? Why not make that easier? Why not say, okay, here we have our network. We're going to be taking this switch down. We know all of the dependencies upon this switch throughout the graph all the way down to the users. Let's notify the users that the applications that they depend upon will no longer be in operation for that maintenance period. And similarly, a lot of folks use this for, they see 6 things down in the network and they want to know what those 6 things have in common in order to figure out what to investigate to bring it back on as quickly as possible. Now, tracing down to those users oftentimes involves identity and access management. It oftentimes involves understanding who the users are in your system. And so Neo4j is used a lot for this, to manage the permissions, manage group membership and how the groups all interrelate. Typically, this is done through something called LDAP, or Lightweight Directory Access Protocol, I believe. I might have just made up the definition of that acronym. But typically it's done through LDAP, which is a strict tree hierarchy. I've worked in organizations where the organization is definitely not a strict tree. It's much more of a graph. Actually, I think every organization I've worked in has much more of a graph than a strict tree hierarchy. So it makes sense to store this in graphs so that you could make real-time decisions. We have customers that moved off of batch processes where they calculated the access to various resources every 12 hours instead of doing it real time, because it was just too expensive to understand who has access to each and every resource in real time. Then they move to a graph and they're able to make those decisions in real time. So now when people are fired or hired, their access rights to individual resources are either removed or granted. UBS has actually based a solution for identity and access management on top of Neo4j. So I talked about use cases. Verticals, pretty much every vertical in the world uses Neo4j for these types of use cases. And there are major companies here, and that, the vast majority of our enterprise customers are in this sort of global 1000 space, and they're really recognizing the value of the graph and what the graph can do for them across these various use cases. So now I got to the agenda slide. We're 33 minutes into the webinar. I talked about use cases. I'm going to talk a little bit about the pain that your SQL developers go through, and then I'm going to talk about building a Neo4j application, as well as moving between the different types of models and how you might make the decision about how to model your graph based off your relational data. And if I have time, I'm going to get into a few other topics here as well. In the upcoming slides, you'll see a lot of drawings. I hired this young gentleman to do these drawings. I promise that the handwriting is not mine. I write much better than what you will see. So day in the life of a relational database developer. See the young child's handwriting right here. And in a relational database developer, they think of data in these tables, so columns and rows. In this case, we're listing out various people and what country their origin is from, and their hair color, and the university they attended. And if we go to normalize this, as we're all taught in computer science classes, we take the countries and we make them into these separate tables with auto-generated numeric foreign keys, so we can update the name of the countries or the abbreviations, which, believe it or not, does happen quite often. And we can also associate other data with those countries, like the leaders of those countries. As you can see, at least for the US, actually for the US and the UK, this is a little bit old. Not sure on China or Israel, but we can identify each of the leaders here. And then our main table here looks something like this. We have these auto-generated numeric foreign keys pointing from the country column here to the various countries and their metadata. And we can do the same thing for universities, create a separate table and then reference that separate table. And that allows us to achieve a lot of consistency. but it does make the readability of this table a little bit more difficult. In the end, we have these three separate tables. Anytime we want to do a query to understand the data that was in our first table, we have to do joins across these three separate tables. So at least 3 joins per row in the types of people we're interested in. But it could be, many more joins operations as well. But your SQL query would look something like this. You would have joining your first table to your second table to your third table. And this isn't too bad. I've worked with SQL for many years. This is readable. You can kind of understand what's going on here. But many of our customers don't just have a handful of joins. They have 15, 20, 30 different joins in their SQL statements. And that's where the performance of doing those joins gets super expensive, and the value of index-free adjacency in graph databases gets more and more valuable. And when you have 15 or 20 different joins, then your developers are thinking about joins all day long, all night long, and it's keeping them up at night and preventing them from getting as much sleep as they otherwise would. Slight conjecture here, but I know that I definitely laid in bed at night thinking about my SQL statements and how to optimize them at one point in my life. And I started optimizing them things like indexes, and those indexes were great, but they still had that problem where if you're doing many 15, 20 different joins, different tables, joining those together, you're doing lots and lots of index lookups. So what we do as developers is we say, oh, well, forget about what you're taught in computer science class. Let's denormalize all of our data. And so you store data in some form like this. And that makes it more difficult to maintain your consistency in all of your data. If you do keep your data properly normalized, then your queries get long and complex. Everything becomes kind of painful. On the graph side, it's pretty easy to model and store those relationships. The performance of traversing relationships becomes constant, or is constant, with the growth in overall data size, and that's due to that index-free adjacency. The queries with Cipher, which is now available as an open protocol called, or an open language called OpenCipher, and other database providers that are working with graphs are starting to adopt it. Queries with Cipher are shortened and more readable. And then we talked about you can add and remove things on the fly. So John Resig may not be as famous as, say, Obama, mentioned in our earlier slides, but John Resig is someone who builds code that you use every single day. I guarantee you that if you browse the web for more than 30 seconds on any given day, you use code that is written by John Resig. And that's because he created jQuery, which is one of the most popular JavaScript libraries on the internet. And he said, really digging Neo4j, what used to be a handful of complicated analysis scripts are now, what used to be a bunch of complicated analysis scripts are now a handful of simple Cipher queries. And that's really the value of the language, is making it lives easier for you as business folks as well as developers. As business folks, because you don't have the translation between you and your developer in the data and how the data is represented. And as developers, because you can explore your data using a language that's fairly simple. So I'm going to go through a basic graph here. And our graph is about Anne, who loves Dan. And I actually switched the direction here in the next slide, or switched the gender, one of the two. But in this case here, Dan loves Anne. And so we're going to create 2 nodes, a node that is a person labeled node. This is sort of the type of node, it's person. And another node that is a person labeled node. And we're going to assign name properties to each of them. So on the left, we have a person labeled node with a name of Dan. and on the right, a person labeled node with a name of Anne. And then we're creating, with Cipher, the relationship between these two nodes as well. So we're saying Dan loves Anne. And you notice that arrow there? We call that ASCII art for graphs. Basically, you are drawing out the relationship using keyboard characters between Dan and Anne. And so your relationship here is created along with these two people in this one simple line. So this one simple line of Cipher, you're creating Dan, you're creating Anne, and you're making them fall in love. You'll notice that the relationship is a direction. Relationships in Neo4j are always directional. You can query without regard to direction if you choose, and that's just as efficient as querying with regards to direction for the same number of relationships. So if we think about the earlier model where I talked about people and their hair color and their university and things like that, the model might look something like this. We have a person, again, this handwriting is from that young gentleman, not myself. We have this person who lives in a country. That country or state is located in that country. The person went to a university that is located in a state, and the university is led by a leader. Notice how I just read through this. You can read through a properly designed graph model as English phrases really easily, or French phrases or German phrases, whatever language of your choice, but it's very easy to read through because the nodes represent nouns, the relationship represents verbs, and then you have properties on the nodes, such as Anne's name. Those are the adjectives. And then you can have properties on relationships that are kind of like the adverbs. And then when you're doing a query, instead of the join, you're going to query like this. And you can read through this line by line and understand exactly what's happening here. We're matching a person who went to a university. We want to figure out what country that person lives in. We want to figure out what leader leads that university. And we want to figure out what state that university is located in. And the rest looks similar to you if you're familiar with SQL. So here's another lovely quote from the internet. I love Neo4j because I can explore relationships faster than you can say SQL join, Neo4j. Now, David Meza is not a household name. You probably do not use his code every single day. You may see some of the projects he works on every single day. David Meza is the chief knowledge architect for this little organization we call NASA. And as the chief knowledge architect at NASA, basically what he is trying to do is learn from all of NASA's past successes and past mistakes in order to do the space exploration of the future, in order to get us on Mars. So you can think of David Meza as being a forerunner for our technology industry, and he loves graphs. And you know, this is something that we find more and more often. As soon as people discover the graphs, discover Cipher as a query language and start using it, they really see the power in it. So you use Neo4j by creating a model, loading your data in, and then querying your data. Now, querying your data. How does that work out? Well, Neo4j has a thing called the Neo4j browser. This is an application, a web application that is part of your Neo4j install and allows you to write queries and execute those queries on your graph and get results back either in a tabular format or in a graph format, depending on what you're looking for. It's an excellent tool, but it is a developer tool. It's meant for your developers. So most people don't give the developer tool to the end users. They write applications on top of Neo4j using one of the official language drivers, JavaScript, Java, .NET, or Python, or some of the community-written language drivers such as Ruby, Haskell, Go, and PHP. They write their code that interacts with the graph database simply like you'd write your code that interacts with any other type of database, and they build applications. Now, if they want to explore their data beyond using Cipher, so for each of those language drivers, you pass it Cipher queries. You can explore your graph directly within Java, as an example, and you can create Java stored procedures and functions that execute inside the database and shave off every last millisecond of performance hit that you may get by having us interpret what you're trying to do. You're just basically coding, here's how to traverse the graph, and we say, okay, we'll traverse the graph that way. And there are a whole bunch of Java stored procedures and functions out there, hundreds and hundreds of them, that add features and functionality to Neo4j contributed by the community. And many of those are in a library called APOC, which we're going to talk about here soon. I do want to encourage you all to get started working with Neo4j today. This is the Neo4j sandbox. It is an application which I've written over the last handful of months. And I mentioned it earlier. Basically, what it allows you to do is to explore graphs by choosing a particular use case. So you can choose to explore graphs with a data set based off of recommendations, or with a data set based off of US legislation, or a database or a data set based off of the connections between Trump and all of his cabinet members and the government contracting database and things like that. So there are a variety of data sets there. We're expanding more and more of the business data sets like the recommendations one. But not only do you have a variety of data sets available there, but you also have guides that guide you through those data sets. So like I was talking about with recommendations, it shows you how to perform a number of different types of recommendations on that data set, which then you can apply to your own data. And so this gets you a copy of Neo4j running for just 3 days in the cloud. You can extend it up through 7 or 10 days as well by just filling out some additional information. But it gets you up and running. It gets you an instance of Neo4j within probably 30 seconds or so. And you get to play around with it. And not only can you play around with the Neo4j browser, but there's also code snippets for each of these use cases there for many different languages that you can copy and paste and execute and start building your applications. Now, this gentleman is not famous at all. I'm not going to try to make up some sort of case about it. Maybe he's famous because he's amazing in the Neo4j community. But he says, I can't believe that Neo4j is actually real. Seems like a dream come true. Now, we're not going to say that you should take Neo4j and replace all of your database infrastructure with Neo4j. We believe in the concept of polyglot persistence. We believe in the idea that you should be able to understand your data needs and understand what types of databases best suit those needs. And for each type of application or each feature in your application, use the databases which make the most sense. So you can have your Neo4j cluster, you can have your other types of relational or NoSQL databases or Hadoop clusters, and you can have your application using all of these for your real-time decisions and basing your application. And you can also use all of these for your analytic infrastructure and have your data scientists look at them. Neo4j is designed as OLTP, ACID compliant. It is meant to be your primary data store for your data, but it also can be used for analytics, and a number of our customers do that. And so you can either migrate all of your data to Neo4j from your relational database, or migrate a subset, or duplicate a subset, and the application developer decide which database to access. So quick scenario here, running through converting a ER diagram here to a to a graph model. We have all of these tables. This is the Northwind data set, which you can also find in the sandbox. Just launch a blank sandbox and go through the getting coded section or start coding section, and you'll see some of the Northwind data guides there. But this is the Northwind data. It's basically categories, suppliers, products, orders, employees, and it's how all these interrelate. ER diagrams to me make me a little sad because they're a little bit hard to read. They're kind of like a graph, but we're going to show you that Northwind, the canonical relational database example, will be better as an actual graph. And that's because you can read it. So an employee represents a territory, and that territory is located in a region. An employee sold an order, which includes a product, which is supplied by a supplier. You get the point? So Northwind is better as a graph. So let's show you how that works. So if we start with that ER diagram, we then locate all of the foreign keys in the database. So how the orders relate to products, how the employees relate to employee territories. There are all these foreign key relationships. We drop those foreign key relationships and create actual relationships in their place, relationships in the graph world. So the details relationship, the employee relationship, the territory relationship. And then we find these join tables. And these join tables are things like joining a order to the details of all of the different products that are in that order, the price, the quantity, the discount, or joining an employee to a territory. And the very simple join tables, like the employee to a territory, we don't need the kind of intermediate table here, the join table. We can just represent that as a relationship called represents. An employee represents a territory. And then for the order details table, I'll call that an attributed join table. And the attributed join tables simply becomes a relationship with a set of properties on that relationship. So an order includes products, and for each relationship between that order and a product, we have a unit price, quantity, and discount as properties on the relationship. Okay, so I am going to go through simply a handful of queries here, and then we'll give you 2 minutes or 3 minutes to get the most important questions answered. Sorry, there's a lot of material here, but again, you can reach me at ryan@neo4j.com if you have follow-up questions, or on Twitter at RyGuyRG. So who do people report to is the most basic query. So find me an employee, we'll call it a subordinate, that's just an alias, SUB, reporting to another employee, and return that, and that returns a graph. And if we want to get a little bit more detail about those people and return it as a table, so you can process it as you ordinarily would process a table, you can do that. And so you're returning specific properties of the employee and returning those as a table. And let me get to a little bit more complex one, and you'll get the slides for this. You'll be able to go through some of the other examples. But what is Robert's reporting chain? And so you can see here, Robert, we're saying, is the subordinate. SUB is our alias. We're saying his first name is Robert. And we're saying Robert reports to star employee, and find me that complete path. So that will traverse any number of reports to relationships and find me the full path and show me who Robert reports to. And let me quickly advance. 1 second here. So importing data into Neo4j, how do you get started here? You basically import your nodes, create the relationships, or sorry, create indexes, and then import your relationships. I'm not going to go through each this line by line, but there's different ways to import data. Load CSV is the easiest, but it is transactional. But you can specify here the Cipher statement. So basically, for each row of the CSV file, here's what action to take: either create a node or create a relationship. And so I'm going to skip over that and briefly touch upon two other ways that you can load your data into Neo4j. There's a Neo4j import command line tool, which is super fast. We loaded 4.5 million things and their relationships in 100 seconds. That skips all of the transactional overhead and just creates the Neo4j database files. But then the other thing that you can do is load data with JDBC. So APOC is a library of those Java stored procedures and functions that I was talking about, and it has a load JDBC in it. Search for APOC on the internet. This is an open source library contributed by the Neo4j community, and you'll find in it the ability to load stuff from JDBC. So here's a quick example. In this case, I'm loading the MySQL JDBC driver, and then I'm calling over from Neo4j. So I'm writing this Cipher statement that calls from Neo4j over to my MySQL database and gets the data from my MySQL database, and then creates the nodes and then creates the relationships directly using JDBC. So this is definitely a way I would encourage you to take a look at understanding your data. You can do this if you download Neo4j. I don't yet have this MySQL driver in the sandbox. I do have APOC. The whole library APOC is available to you in the sandbox. The MySQL driver isn't quite there yet, but if I figure that out today, then when we send you the slides and video, I will let you know if we figure that out. And that is all I have. And remember this quote here. We found Neo4j to be literally thousands of times faster than our prior MySQL solution, with queries that require 10 to 100 times less code. Thank you.